There's an engineering challenge in building quantum computers, which is how to store information in the memory of the quantum computer safely, robustly, because quantum computer memory is notoriously susceptible to any interference from the outside environment.
Hey there, space enthusiasts. Get ready to blast off into the cosmos with us. Welcome to Spaceverse, where the universe is our playground and curiosity knows no bounds. Join us on an interstellar adventure as we dive into the depths of space, uncovering its mysteries and marvels. From the secrets of black holes to the landscapes of alien worlds, we're here to ignite your imagination and expand your cosmic horizons. With mind-blowing visuals, expert insights, and the thrill of exploration, Spaceverse is your ticket to the ultimate cosmic journey. So strap in, hit that subscribe button, and let's embark on an epic voyage together into the vast unknown of Spaceverse. Explore the world of theoretical physics with Alice and Bob, two well-known explorers who are famed for their explorations. People who believe in the thought experiment, also known as the Jettinkin experiment, whose purpose is to find flaws in our most fundamental theories in order to go deeper into the topic. On this courageous day, our daring pair will take a leap of faith and dive into a black hole. To get knowledge regarding quantum entanglement and the fundamental structure of spacetime, it is necessary to study. In both recent and older cases, it has been demonstrated that the notion of black holes can inspire odd ideas. That every piece of information about a specific volume of space may be contained within its borders is one example. Another example is the notion that there is a minimal meaningful distance in space. In addition, we made a fundamental observation regarding the manner in which that boundary can encompass an entirely new spatial dimension, which led to the conception of the electromagnetic universe. At that distance, on the other hand, we consider the possibility that gravity could be a consequence of thermodynamics. We had a conversation on the idea of embedding the emergent dimension in the scale of border patterns in 2 episodes that came before this show. Modern physicists working in this area, on the other hand, believe that quantum entanglement, which refers to the subtle correlations that exist between the bits of quantum information that describe the properties of particles, offers a more effective answer. To be more exact, as we will see in other episodes, it is beginning to appear as though entanglement is the very fabric of space. This means that space is knit together from the network of mutual information of its components. Alongside the evidence for the least Planck length and the holographic principle, the concept of entanglement's function emerged as a result of the consideration of black holes. In particular, while taking into consideration the fate of quantum data while it is contained within a black hole. When all is said and done, this will lead us to a significant connection between wormholes and entanglement in the R=PR hypothesis. Additionally, the same line of thinking will lead to black hole complementarity, which will completely mislead our intuition regarding the locations of quantum information. Black hole complementarity is a very interesting concept. On the other hand, the contradiction that lies at the heart of everything is something that we intend to establish today. The only way for it to occur is if Alice and Bob are willing to take the plunge into the abyss. To be more precise, it is only Alice. Over the course of her life, she has always been a little more bold than Bob. Therefore, Alice and Bob travel to the supermassive black hole that is located in the Milky Way, which is designated as Sagittarius A star. Alice puts on her jumpsuit as she gets ready to attempt the leap. Bob puts himself in a position to maintain his distance and observe. Alice is wearing a clock that emits regular pulses of high-energy gamma rays so that Bob may track her whereabouts and observe how the passage of time affects her. Bob is able to do this because Alice wears the clock. Alice also possesses a container that contains 1 electron with its spin locked. This electron is contained within the container. This is where our qubit, also known as a quantum bit, is located. In this case, the information belongs to the orientation of the spin of that electron, namely to whether it is oriented upwards or downwards. A further feature of the box is that it may be independently tracked by generating gamma ray pulses at regular intervals. Her excitement at being the first person to glimpse beyond an event horizon causes Alice to give Bob a high five before diving headfirst towards Saga Star. She then throws the qubit box to fall slightly ahead of her as she begins to plummet. The first thing we'll do is examine it from Bob's point of view. Through the use of his gamma ray telescope, he determines the passage of time while simultaneously monitoring Alice and the box's descent. Through the process of gravitational time dilation, the gamma-ray photons undergo gravitational redshifting, which causes them to stretch to longer wavelengths. Additionally, they arrive with increasing separation. In addition to this, Bob has triggered detectors that are sensitive to 3 different wavelengths: radio, visible, and X-ray. As he settles in, he prepares himself to witness Alice's pace slow down as she approaches the event horizon. He anticipates that her seconds will turn into hours, years, or perhaps millennia from this point on. There are no occurrences of that kind. In contrast, he observes Alice's descent towards the event horizon of the black hole, during which she first accelerates, then suddenly slows down, and then converges with it. As time dilation becomes closer and closer to infinity, what happens to the event horizon? It is true that regardless of the type of black hole, it is possible to calculate the distance from the event horizon using any extremely significant time dilation, a time span that can run anywhere from 1 millisecond to 100 trillion years. On the other hand, by the time Alice arrives at these spots, she is already falling at an astounding rate so quickly that she is just about to touch the speed of light. While the amount of time spent at each point is decreasing, the amount of time that is being spent is growing. When Alice and the box are getting close to the event horizon, it seems as though their descent slows down and stops, which is a sign that Alice has won. Bob notices the box slow down and freeze before Alice does, giving the impression that Alice catches up to it. And because Alice's head comes down before her feet, she seems to flatten out from Bob's point of view. On the other hand, Bob was concerned that Alice could become spaghettified, extended, due to the fact that the tides would be acting more forcefully on her head than her feet. Unfortunately, that isn't the case here because the only place where a black hole of this magnitude would experience tidal pressures on a human scale is at its innermost recesses. What actually happens is that Alice's whole body is slightly above the event horizon by the time her head is somewhat above it. Bob thinks the word pancakeification could describe this phenomenon, even though no such word exists. Both the intensity and the wavelength of Alice's photons are now far lower than those of the cosmic microwave background. Even with Bob's enormous radio antenna, they are scarcely audible. After that, Bob completely loses his vision. As he blinks out, he sees the experimental qubit and all of Alice's qubits jumbled together above the event horizon. At this point, Alice's light is nearly identical to, if not identical to, the black hole's Hawking radiation. The non-zero temperature of a black hole causes it to emit a faint glow known as Hawking radiation. Hawking photons with wavelengths exceeding 100 million kilometers are produced when the temperature for saga start exceeds 10 circumflex 14 Kelvin. Bob is doing his best to keep the experimental qubit under constant supervision. However, gathering all the Hawking radiation that the black hole will release in the future is the sole option. He starts building a Dyson sphere-style detector to encircle the black hole in its entirety. In addition, he prepares himself for the long haul by uploading his thoughts to the ship's computer in the hopes of surviving this black hole. Let's take a look at Alice's experience from her perspective in the meantime. The descent into Saga Star happens over the course of a few hours, although by that time it is typically well beyond the event horizon. As a result of her rapid acceleration, the final leg of the journey passes by at a rate that is exponentially faster than before. Regrettably, neither the acceleration nor the tidal forces exerted by the black hole contribute to the G-force. As Alice falls into an event horizon that is substantially larger than her, she has this sense of feeling as though she is not carrying any weight. The equivalence principle proposed by Einstein states that observers who are in free fall see the identical behavior of their local patch of spacetime as if there were no gravitational field at all. Alice is able to detect a large black surface underneath her, which she identifies as the black hole. The surface appears to disappear as she approaches, which is a peculiar phenomenon. It is because of the photons that are attempting to escape the infinite gravitational redshift of the real event horizon that it appears black when viewed from a distance. This redshift is the result of the gravitational well of the black hole being fully stretched beyond its original boundaries. Due to the fact that Alice is so far into the gravitational well, she is still able to come into contact with photons that were released just a little bit above the event horizon. She is not merely passing the time by, waiting for people to approach her, rather she is actively connecting with those who are approaching her. Due to the fact that Alice is moving at an incredibly high velocity, the photons that are pointed outward and that she passes through experience a d-redshift as she comes closer to the event horizon. She can make out the trail of falling objects in front of her, in addition to the qubit box that is in front of her. If we look at the experiment from Alice's perspective, the most significant part of it is about to start. Regardless of whether or not her reference frame displays any evidence of the actual event horizon in front of her, the qubit box will inevitably pass over at some point in the future. When she looks at the box, does she still see it? However, what she sees is the box in its initial state, just before it crossed the horizon that she was viewing. She will not be able to collect photons that have been released by the box from below unless she can personally cross the horizon. Because she is, at her core, a scientist, she switches her attention back to the experiment and smashes over the event horizon. On the other hand, nothing extraordinary takes place. Keeping the equivalence principle in mind is important. By conducting experiments or making observations on a specific region of space, it is revealed that there is no way to establish whether or not that region is free-falling or free-floating using any method. Due to the fact that this principle serves as the basis for general relativity, physicists experience a great deal of unease if there is even the slightest possibility of breaking it. In the event that we need to break it at a later time, you should also feel unhappy about this, so keep it in mind right now. Alice, on the other hand, will not be able to observe a freeze at the event horizon because the equivalence principle states that she cannot. Neither the qubit nor she was involved. She is likewise unable to arrive at the qubit in the allotted time. While she is looking over the horizon, the qubit is still moving underneath her, and it is making its way towards the dark surface that is always visible below. The gloomy surface, on the other hand, is growing and wrapping itself around her at this precise moment. Following the closing of Alice's up irises, the universe that surrounds her transforms into a constricting down, and any and all directions gather together to form a singularity at the end of space and time. In spite of the fact that Alice is unable to leave the room in order to inform Bob of the results of the experiment, she still thinks it to be a very successful endeavor. As of right now, she is aware of the fact that black holes are capable of consuming quantum bits. Now is the moment to go back to Bob. It is important to keep in mind that he is now working on the detection of experimental qubit signals as well as the pursuit of Hawking radiation. On the other hand, if we are to be absolutely honest, he is also striving to locate Alice. Light is emitted by a black hole. As a result of this, it would lose mass if it were not ingesting more cosmic microwave background than it is emitting forth. Sagittarius, a star, begins to constrict after approximately 100 billion years, when the expansion of the universe has decreased the cosmic microwave background CMB to a temperature that is lower than that of the black hole. This is assuming that it does not heat anything else. Even Bob is aware that the black hole will be destroyed by this radiation at some point in the future. Additionally, as a result of his exposure to classic episodes of PBS Spacetime, he is familiar with the black hole information paradox as well as the concept of conservation of quantum information. Because of quantum mechanics and possibly even his own feelings, he will not be able to remove Alice's data or the experimental qubit from existence. Following in the footsteps of a large number of other physicists from the 21st century who have since passed away, Bob arrives at the same conclusion. The information must be contained within the Hawking radiation. On the other hand, this might take place if the black hole vanishes into nothingness. The Hawking radiation appears to be completely random after an infinite number of cosmic lives have passed. For Bob to be able to store and analyze all of this information, he had to build a number of star-sized computers, which are also frequently referred to as Matryoshka brains. In all honesty, nothing significant because Bob is completely and utterly bored. When the black hole has lost half of its mass, it will be 1087 years later. At that time, all of the stars will have died inadvertently, and their stellar remnants will have dispersed throughout space. Bob and the black hole are the only ones that are left at this point. In the aftermath of that, Bob investigates the ensuing data of poor Hawking radiation, but this time he sees the first evidence of a slight pattern. The most minute of connections are starting to show up among all of the earlier radiation, which suggests that there is a highly garbled order in the chaos of the bits that are stuck on the event horizon of the black hole. Even more captivated by his collection, which appears to be inexhaustible, Bob continues to move forward. Upon regaining possession of the quantum bit, he will demonstrate beyond a shadow of a doubt that black holes do not have the ability to take in quantum information. Not only does Bob learn the reason for his extraordinary patience just before the black hole vanishes entirely, but he also manages to retrieve all of Alice's former components. In order to digitally reproduce Alice's mind, he makes use of the entire capacity of the enormous Matryoshka brains that are fueled by black holes. They are then reborn as digital ghosts in a universe that has been destroyed, and they live happily ever after. A happy conclusion for Bob in the Alice version encoded on the event horizon, but not for the one that fell in or for physics, despite the fact that it could appear to be the case at first glance. We will continue with our experiment like we did before. Can you tell me what happened to the qubit in reality? While it was still on the horizon, Bob was able to catch a glimpse of it shortly after it manifested itself as Hawking radiation. Alice, on the other hand, was present during its plummet below the horizon and eventual merging with the singularity, which occurred just before she followed in its footsteps. When it comes to physics, one of the most popular ways to develop a hypothesis is to uncover contradictions within it. This is certainly the greatest significant advantage that may be gained from the Jettington experiment. It would appear that we have discovered a contradiction here. There are two very different inferences that might be drawn from the question, is the qubit still around? Instead of simply asking, what is the whereabouts of Alice? We choose to employ a qubit for a purpose. Reason being, qubit technology makes our contradiction more pronounced by enabling us to violate very particular laws of quantum mechanics. Bob came to the conclusion that the qubit has to be kept in Hawking radiation because of the limitation against erasing quantum information, which I have already discussed. The no-cloning theorem, however, asserts that quantum bits are irreplicable. I don't understand how the bit could be within the black hole if it exits in Hawking radiation. Copying or erasing quantum data is problematic because it violates unitarity, a property that is as basic to quantum physics as the equivalence principle is to general relativity. A description of probability is given by the quantum wave function. Each probability must sum to 1. The sum of all the possible positions of an object cannot exceed 100%, since that would have no practical purpose. It is forbidden to delete or duplicate qubits, since doing so violates unitarity. It appears that in order to break unitarity, we must either delete the qubit when the black hole evaporates or duplicate it in the Hawking radiation. Alternately, we may assert that Alice and her bit never transcend the event horizon, thus violating the equivalence principle. It will take another week before you can determine which is true. Just a week isn't too horrible considering Bob waited for 1087 years. We will next begin to examine a number of potential answers to this contradiction, including black hole complementarity and the firewall at the event horizon. We will keep refining the methods that will allow us to weave entangled qubits into spacetime itself. A heartfelt thank you for being here with us today as we come to the end of our journey at Spaceverse. Your support is what drives our investigation of the cosmos. Remember to hit the notification bell and subscribe to our channel so that you can continue to explore with us. See you until the next time we cross paths in the cosmos.